And this is discussed in more detail in the project document. I would recommend that you have a look at the project document. It's on the course website. You can download it. And it discusses this idea of using a root finding approach for design. So what we really want is we want to find, in this case, a diameter that gives us a deflection then that matches the allowable deflection. So in other words, we want to find a diameter such that the deflection is equal to y allow. And we can rearrange this equation into a root finding form, or in other words, we want to find where this equation or this formula is equal to 0. And graphically we can think about it this way. So if this is the diameter on the horizontal axis, and I don't know exactly what this is going to be shaped like, so as the diameter gets bigger, the deflection is going to get smaller, so it might look something like that. And this curve right here, that represents this y of d minus the constant y allow. And where it crosses 0, that is our diameter that's going to give us this desired level of deflection. So that's what we mean by a root finding approach, and this iterative formula, it helps us to try different values of diameter until we hone in on the correct value that gives us the right deflection. So in thinking about how design is the inverse of analysis, this is a good example of that. In simple cases for shaft design, we can invert the analysis formulas and solve for the design variables. So in this case, d, the diameter, would be the design variable. And if you remember, earlier in class we looked at a graphic that described this idea of how design is the inverse of analysis. So if we invert an analysis formula, sometimes we can come up with a design formula. If we are performing analysis, we're going this direction from left to right. We start off with the system specification, maybe something like a CAD model or other parameters that fully define what the system is. We perform some type of analysis, whether simple analysis like we're doing right here, or maybe something more sophisticated like finite element analysis. And this analysis helps us to predict how a system is going to perform given the system specification. So we're interested in some type of performance metrics. In the case of shaft design, we are interested in stress or fatigue properties or deflection, and later on we're going to talk about vibration properties of shafts as well. So if we want to do design, however, we're starting off with some desired performance metrics, and we go the opposite direction. We have these desired performance metrics. We need to somehow invert the analysis and come up with a system specification. In simple cases, we can invert the analysis formulas directly and come up with a design formula. But in more complicated cases, we can't do that. And so we need to use some kind of iterative approach, and this root finding approach is one possible approach for solving the design problem. What we've just gone through, this iterative formula for shaft design, we could see as an application-tailored root-finding algorithm. There are general root-finding algorithms, such as Newton's method. Well, this is a special root-finding algorithm that's just for shaft design. So there are some cases in design where we can use these application-tailored root-finding algorithms. But in other cases, we might just use a general purpose root finding algorithm such as Newton's method or the secant method. One example of a general purpose root finding algorithm is in MATLAB. If you put something in this form where you want to find where a function is equal to 0, you can use the MATLAB function fsolve. Let's talk for a moment about angular deflection in shafts due to torque. So earlier in class we did a quick review from Chapter 3 regarding angular deflection and shear, and one of the formulas that we went through was this, where theta, the angle of twist or the angular deflection, that's going to be equal to the torque times the length of a shaft divided by the shear modulus times the polar area moment of inertia. So if we have a constant diameter shaft, then we can apply this formula directly. But let's look at what happens if we have another case where we have multiple diameters. So we can decompose the problem then. The total deflection for the shaft is simply going to be the summation of the angular deflection of each segment of the shaft that has a constant diameter. So if we decompose the shaft into, say, 3 segments, each with its own constant diameter, we can solve for the deflection in each one of those segments separately, and then sum them all together to get the total deflection. So we can apply this formula, and so for each segment I, we have the torque at I times the length of segment I divided by the shear modulus at I and the polar area moment of inertia at I. So some of these things are typically constant. Often we use the same material throughout a shaft, and so this shear modulus is going to be constant. If we do not have any, say, gears or belts, pulleys in the middle of a shaft, then the torque is going to be constant. But the things that are often going to be different are the lengths of each segment and the diameters of each segment, which of course influence the polar area moment of inertia. So we can pull out the constant terms, torque over the modulus, and then multiply by the summation of L sub I over J sub I. So this is a formula that you can use to evaluate angular deflection, the total angular deflection of a shaft, as long as the torque is constant throughout the shaft and you're using the same material, but it accounts for different lengths and also different diameters. So you might wonder, well, what cases would angular deflection be important, or where does it show up? So here's one example from the automotive world, and this is something a lot of you are probably familiar with. If you were to park a car, put your gear shifter into park, and then let off the brake without engaging your parking brake, you might notice your car moves just a little bit, especially if you're on a hill. It might roll backwards just a little bit and oscillate just a little bit. And there are many sources of that deflection, but what you're experiencing is angular deflection in the drivetrain that connects the engine to your wheels. So when you put your car in park, there's something in the transmission that locks the output shaft of the transmission in place, but then you still have a drive shaft, you have a final drive, you have all of these components in between your transmission and your drive wheels, and these components can flex just a little bit, and some of that flexing is angular deflection of shafts. For example, the angular deflection of the drive shafts. So that's one example that you might be familiar with. Here's another example that's important from the automotive world. Earlier in class we looked at a video that showed some animations of the internal mechanisms of an automotive engine. It involved things like a crankshaft and a camshaft and push rods and timing belts. So the camshaft, its job is to open and close the valves that let the fuel-air mixture into the cylinders, and then also open the exhaust valves that let the burned combustion gases exit the cylinders. And it's really important that these valves are opened and closed in a very precise way. So as the camshaft rotates, if there's any noticeable deflection in the camshaft, then that's going to affect when the valves open and close. If there's a lot of deflection, it's going to delay valve opening and valve closing. And so that's something we really need to avoid. It's very important that a camshaft does not have too much deflection. To summarize, there are 3 types of deflection in shafts that we really need to pay attention to. One is a transverse or radial deflection. This is very important at places on shafts such as where gears are mounted, or also places where we might have interference between the shaft and other mechanical components. Second, angular deflection is important for us to pay attention to. We discussed how it's important for us to make sure angular deflection does not exceed recommended limits for bearings. It's also important for cases where we are meshing gears. We also discussed angular deflection due to torsion. This is very important whenever we need to produce a system that has precise motion. We gave the example of an automotive camshaft. That's a system that requires very precise rotational motion.